Well, today I'm going to begin on the topic of optical fibers. It's a problem which is important, but the real reason is that I lived through the period when it arose, became popular, and therefore I can tell you more or less what I did. It is typical of a situation you will meet many, many times. New areas come up. You have not the time or the energy to become an expert, but you cannot afford not to know. If you don't learn about some of these fields, the world will pass beyond you and you'll be left behind and rather unhappy. So this is really the example of how one particular topic I handled. Well, it begins by me noticing on the bulletin board that there is a talk on optical fibers going to be given. It's an interesting topic, but if you're going to work at a place like Bell Labs or MIT or someplace else, there's always interesting lectures going on, and if you don't do your own business, you'll spend all your time learning something but never doing anything. So it's always a problem. Do I work on what I should be doing to help the company, or do I go out and learn something more so I'll be useful later on? Well, let's review what I knew before I went to the first talk. Having had lab courses, I knew you could draw glass out to very fine fibers. I also knew that they were very, very round because the surface tension of liquid glass is rather high, and so it grabs the smallest circumference, which means it's going to be circular. Another, I knew that optics was very high frequency as against electronics in those days, and that the business of the telephone company was bandwidth. That's the name of the game. Clearly, there was much more bandwidth in optical frequencies than there are electronic frequencies. Tremendous amount more. So we could send more information. Lastly, I knew a curious fact that Alexander Graham Bell actually had built some equipment and sent a voice over a light beam. It was a big kludge thing. It was just a light beam, wasn't glass fiber, but he had done it, so it could be done. Oh yes, one more thing I knew. I knew about internal reflection, that if you come from water up to air, it'll come out, but there are angles which you go out and there's total reflection back, that if you look a sufficiently slant from below the surface of a smooth pond, the light will reflect it back into the water. Same way, if you're in glass and you have a very slow, slight glancing angle, the light will be totally reflected back into the glass fiber. So you see immediately, when you think about that, you want a small fiber. You don't want a fiber to get a good size angle at the surface, but you want it so small it must always skim the edges. That's why we make small fibers. Well, I went to the talk because I said, it's bound to be important to the telephone company, and I'm bound to get problems on the subject to calculate, so I better know something about it. The first speaker said, God loved sand. He made so much of it. What I heard was, if we go to glass, we won't be like we are with copper. At present, even those days, we were mining poorer and poorer copper mines, doing more and more work to get less and less copper. Well, you aren't going to run out of silica. Not likely. Either the next lecture or the one after that, there was a guy who said, in the ducts underneath the streets and the sidewalks of New York City, we have wires, and those are getting kind of crowded. And if the Manhattan grows as we expect it is, we'll have to dig up a lot of those and put a lot more down, and we'll dig up a lot of streets and sidewalks. But if we get glass fibers, we can pull out the big copper wires and put in small glass fibers, and we can get along for a long time without digging up. Well, that says to me, Bell Labs, if it has to spend $1 million or $100 million to avoid digging up the streets of New York, it'll be a bargain. Bell Labs must work on glass fibers. Not they think it's nice, they have no choice. So I continued following it. Now, one of the things I had learned when I came to Bell Labs, after I decided to stay, that in building electronic gear, which I tried building a few just to see how it went, you do a lot of soldering of wires. Well, you aren't going to solder glass fibers or just fuse them together. Glass fibers, you're going to have to bring them up end to end very, very carefully and keep that intersection contact very well done. So I've promptly put my mind on how will they, in the field, not in the laboratory, in the field, splice glass fibers? Or will every fiber have to be exactly the right length for each use? Well, they came up with quite a few methods, as you know, and we've solved the problem reasonably well of splicing it. But I started looking for difficulties. Well, the first test was done down, as far as I remember, in Atlantic, connecting up two central offices, just simply interconnecting with a glass fiber. And they ran 15 months or something, and it worked out very well. So it was sort of proved in. But then I noticed a curious thing. What they were doing was get the glass fiber signal optically, detect it, bring it down to electronic frequencies, amplify it electronically, convert back to light, and go on. Now that has to be pretty rotten design. So I said to myself, they're going to have to build optical amplifiers. There's no way around it. They've got to do it. And I thought and asked a few physicists questions and decided there were a number of ways this might be done. Therefore, probably one of them would come through, and we would have all optical fibers. So those are the kind of things that went on in my mind. Now, why do we want small ones? Because a small glass fiber, 1/10 the diameter of hair, two things happen. In going down a big fiber, some paths can get longer than others if it bounces from sides. But if it's very, very thin, almost all paths will be the same length, so the various parts will not get out of phase as they go down the line. Secondly, as I go around a bend, if they're very thin, I can make much sharper bends than if it's large, thick. Not that it's bending in glass, but it's a reflection on the outgoing that no photons will get out. Well, then I begin to think some more about these things. You know that it's not too hard to tap a telephone wire that's electronic. You put a coil around it and you pick off the electric field and you amplify it, and you can hang it on the guy's phone and they don't know it's there. But optically, so few photons come out that you can't take the photons which escape and use them for anything. It's not that you could not, but it's going to be a very difficult technical feat to eavesdrop a glass fiber, where it's quite easy, the other one. And another thing, having done some work that I told you with these guys, the upper chemistry atmosphere, do atomic bombs, I was well aware of electromagnetic impulses that come from there, which also come from lightning. Lightning strikes bother copper wires. Atomic bomb will bother the transmission on a copper wire, but they won't affect the glass fiber. So glass fibers had a lot of nice things that came out of it. Another one, there is what they call single mode and multi-mode. Single mode meant you used the basic fundamental frequency. The higher modes meant you used some varying versions of Legendre functions and got the wave across there. So you could send in each one different modes and at the back end separate the modes out and get all those different messages down the same wire. There was some arguments. It was a technical one, but I bet on the single mode because I bet originally on the binary machine. We had tried building in the early days some decimal machines. You know all the machines are binary. Well, I bet on the single mode, and I think that's still what they're doing almost always. So that is sort of what happened along the way and what I thought about it. Now, several other things happened. It was clear to me that if you put a cladding on the outside of the glass, you might affect it so more photons get out, which you don't want. You want to keep those photons in, and they got to go down the line. There's very little loss, only the absorption of the glass itself. Well, they had the idea of taking a good sized glass rod, put another glass sleeve around it of a very different index refraction, heat them up so the outer one shrinks down a little bit. Now I've got this solid piece. I draw it out to a long glass fiber, and of course, that stuff stays there, and I've got a very thin but definite layer of different index, and refraction is going to be happening inside throughout. They could have mirrored the surface, but they chose to do that. Then later on, they decided it was much better to produce a graded change of index refraction rather than a smooth one, and which, if you stop and think about it, it's precisely the technique we use in cyclotrons to get the beam focused. We put a graded field as though those that begin to deviate are begin to pull back. More deviation, more, but there's no sharp cutoff, it's just a tendency to bring them back all the way along. And that can be done either chemically or by radiation. And that's what, by and large, we now do for glass fibers. We either radiate or use some chemical methods to deposit some particles to make the glass a little different index refraction so the beams are bent back and things that go very nicely for very long times. Now, Bell Labs have been working on making better glass, but once glass fibers began into business, the optical companies started getting really clear glass. Now, you would have thought they would have done that for the astronomers. They hadn't really. I am told that some of the glass they can make now is so clear that you could see the bottom of the Pacific Ocean from the surface. Almost no impurities, nothing bothers them. Now, of course, that depends on the frequency you're using. And since we had to use lasers, we had to pick our glass to fit the lasers, although slowly we are getting lasers in almost any band frequency we want. But for a long while, we were restricted to those kind of lasers which we could make. So, there you have the kind of a thing. Strong focusing is roughly what we use now to keep the beams in the middle of the beam. Yeah, let's see, I got along further than I thought I would. Well, all the parts, as you know, did come together fairly well. They are fairly light. Now, when I first came here, the department head, who had been a captain, was assigned as supply officer to the Enterprise, and he invited us for an afternoon and evening wandering around the ship, along with having dinner with the executive officer. I took the opportunity to look at the ducts. And I found all kinds of wires going through ducts, and sometimes there wasn't room to go through ducts, and they ran through doorways which should have been closable in case of storms. Well, it didn't take me long to figure out that insofar as those wires were carrying signals, we could replace them by glass fibers, and just as in the New York streets, we wouldn't have to make more duct holes, we simply put smaller wires through. Insofar as its power distribution, however, that's another story. So naturally my mind says, oh, power distribution. At present, by and large, they seem always to put the power in a central power plant and distribute the power all over the ship. Will they continue? Would it not possibly be better that they would decide to have separate power supplies scattered around here, there, and yon, so no one was vulnerable? Because we're going to undoubtedly put a very redundant glass fiber system through. When there were copper wires, we couldn't. But the glass fibers are so small and have such great bandwidth, we will undoubtedly put alternate paths around from here to there, so that if great damage is done here, another path will be available to get where you want. So long as the receiving end can take instructions you want to send to them. And damage along the way you want to avoid, well, you want to avoid the power distribution too. So you may well decide finally you want many power supplies. I don't know. But it's clear that the glass fibers will replace on a battleship a lot of duct capacity, except insofar as power distribution. Now on an airplane, the same thing, where the weight counts much more. The weight on the Enterprise wasn't that high. I could see that the weight of the copper versus glass would matter much. The Enterprise is just too big. In case you haven't been on it, it's big. For an airplane, however, it makes a big difference. We can greatly decrease the weight of connections. And we can also put redundant systems in so the signaling goes this way or that way to the ailerons. In case some damage is done to part, we still can communicate by the other path or the other several paths. So one sees what's going to happen. Now, we have a thing which we call a drop cord in the telephone business, which is from the telephone pole to the house. It used to be a line in the air. Now many of them are buried. We still call them drop cords. The telephone company is obviously going to go to glass fibers because, you know, they're pretty darn cheap as against copper. Copper is quite expensive. With a good glass fiber, all the information your house can possibly consume could be put on one glass fiber. Your television programs, radio programs, newspapers, everything. As long as you had a print machine, you get the print. But whether that will happen or not is one of the topics which I've talked to you a number of times. Legal reasons, the government not permitting various people to combine, and also the government may very well say at the back end, do we want all the information people can get in the hands of one organized group of people? Or do we in fact want to keep competing one so that every house has several paths in and no one has total control? I don't know. But you see, that's a social problem which dominates the electronic problem. Electronically, putting one glass fiber and everybody sharing it, there's no problem. We know how to do it. What we don't know how to do is do the economics, the psychology, the politics, and so on. So I am not in a position to tell you what's going to happen. I can tell you what could happen, but that doesn't mean it's going to. And it's a very common thing, more and more, that we can do something engineering-wise very easily and very efficiently, doesn't mean we're going to be allowed to do it. There are other reasons. As I said, are you sure you'd like to have one company in control of all the distribution? And if a strike occurs, suddenly nobody gets any information? And so if nobody gets any information, there's going to be no telephone calls, there's going to be nothing except small private radio to communicate. You might not want to do it. Now there's another thing you want to think about is satellites. Around the Earth, about 23,500 miles, right above the equator, there are a bunch of satellites. And they sit up there at that distance because it takes them 24 hours to go around the Earth. The Earth rotates 24 hours, so it sits above one position. But it's got to be right on the equator. We put them now about 4 degrees apart. Now, as we started putting them up, there were arguments. Countries on the equator said, hey, you're invading our airspace. Our airspace goes out to infinity. Well, the wealthier nations have ignored the question. But do they? It will have some effect one of these days. It's not a simple one. Now, we could put them possibly twice as spaced, twice as fine, about every 2 degrees, but if we do that, the antenna on Earth broadcasting up to the satellite must have a much narrower beam so you make sure you hit that satellite. It's going to be much more expensive because if you spread over several of them, you're going to cause trouble. You've got to beam it up to that satellite. Now we can also, to some extent, increase the bandwidth, which we did for quite a while, but after a while the atmosphere through which those signals must go limits the bandwidth you can do per satellite. Now compare glass satellites with glass fibers. A satellite is broadcast. It's broadcast back to Earth to everybody. It's a great broadcast device. Glass fibers are privacy. They go from here to there, and it's very hard for anybody to tap. At present, we are using some of this broadcast business for private uses, but I think that you will find in time that the satellites will use more for broadcast situations, radio, television, so on, and glass fibers will be used for private communication from one person to another. Because we're going to run out of bandwidth going up to satellites and back down again. We're just plain going around the bandwidth because you know how rapidly we're increasing the bandwidth available to you. We're going up very great rates at how much available. As a child, we had radio, a few stations, and we had telephone, not very much, and we had post, and once in a while a telegram, newspapers. We didn't have television and various other things. We didn't have lots of bandwidth you now have and are consuming. And our avidness is going up very rapidly to get more and more bandwidth for everybody. I think you'll find that glass fibers will be the answer for private communication and the other will be for public. Now, you have the quarrel when you discover the telephone company used to, without thinking about it, not when you call the person, you call the position and hope the person was there. In fact, I once, having thought about that, made a remark to a vice president. I said, you know, you don't call people, you call positions and hope they're there. This was many years ago. He says, gee, you're right, I never thought of it. Well, now we are moving toward great bandwidth costs, trying to call you wherever you are, personal telephones. Whether you want one or not is another question. A lot of people do. It makes them feel very important. It's a goddamn constant interruption is what some of us think also. We want to be left alone. It's different people, different things. Let them have what they want. But it's going to consume much more bandwidth and it's going to produce a great deal more trouble, and the satellites will probably be involved in that to some extent. Now we have glass fibers transatlantic, and the one going down to Japan was a very interesting case. There's a thing called a soliton. It's got a peculiar property that it keeps its shape. It goes down the water. It doesn't change shape. Now, if I send pulses down an electric wire, there's dissipation spreading out of the pulse and so on. Solitons keep their shape. They may shrink inside, but they keep their shape. They were first observed, 17 or 1800 in a canal in Scotland. The guy noticed this, and he galloped his horse for 15 miles and saw this wave go down there. And in fact, when my wife and I were up in Nova Scotia and I was giving some talks there, we went out of our way to watch a soliton come up a famous river. It comes up there, goes up this, and it goes up the river, squires around bands and so on. It's just one nice little raise like that. They had been known for a long while, but they were not being exploited. A guy at Bell Labs, a friend of mine, thought that instead of sending pulses, we should communicate by solitons. Solitons, the shape depends upon the nonlinear features of the medium which it goes through, and you can, to a fair extent, amplify a soliton without changing its shape. You simply put some indium or something else up there, you put it in excited state, and the thing goes by, and lo and behold, the thing is amplified. So we have now the possibility, which is curious. We use amplification 10 or 20 stages, and then we stop and reshape or relay a pulse. Now, the time when we were putting down the cable to Japan, my friend had gotten reasonably high rates of solitons, but he was just starting a technique. And the pulse signaling had been long developed. The question came up, which one would they use? And I never found out which one they used because it may well have been just as it did with us on the first voice cable across the Atlantic. Transistors have been invented, but vacuum tubes were known to be reliable. So we put down 3 vacuum tubes every 50 miles across the Atlantic from Nova Scotia to Scotland or Ireland, and they had to have a 20-year life. Any failed tube that really failed was going to cost us $1 million. Well, except for the Russians cutting a cable twice, by accident, you understand, they were just fishing and they just cut it by accident. It's the accepted theory, you can't say anything, it's accepted theory, it was an accident. Except for that, nothing happened at all, no failure, except there was a little bit of bending. The gain at some frequencies was a little higher than expected because the temperature that you use at the bottom of the ocean was a little different than what they thought. At the end of 22 years, we cut that cable off. It was so technologically obsolete that it wasn't worth running. We put in glass fiber since then. And we're putting in glass fibers now most places. Very thin. You people have them. We've made glass fibers shielded with steel around them so you can run trucks and tanks over them. If they're lying in the road, you can run over them and it won't stop it, won't break the glass fiber. We have glass fibers so thin that you can fire them as a rocket and the thing unreels, and you get not only a picture of what the rocket is seeing, but you can also control it. There's two-way communication up and down the glass fiber until it arrives, of course, then everything is busted. Glass fibers have come a long way. We are moving towards solitons almost certainly, which says, I hope to you, all the stuff you learned in electrical engineering about frequency and frequency analysis and so on isn't appropriate for future communication. Solitons are not frequencies. They're a different device entirely. And they're one of the many things I want to call your attention to. You can't afford to become an expert in solitons. You can't afford not to keep track of them. We are by and large putting in solitons in our cables. We're also doing another curious thing which you may not know about. Let's take Africa, the whole continent. What we have done is we've laid a cable in the ocean, running around the whole continent, fairly far offshore. Offshore far enough so we're not going to get in trouble with people on shore. When we pass a country which has a coastline, we send a separate cable in, splice off a cable and send some messages in. Each country on the edge of the ocean gets a message from the central distributor directly, and nobody else can snoop or do anything else along the way. Those inland, well, it's got to go over their land. There's something else again. But we're doing that trick. Now, the reason is very simple, as I intimated. You don't have to dig up a bunch of things or disturb houses or anything else when you lay a cable in the ocean. Furthermore, you don't have much squabbling if you lay it out 40 miles or 30 miles out. It's very easy to lay. We have things now which go along and dig a hole, a rut in, and lay the cable and pull the dirt over on top of it, so it's not laying bare right at the surface. We've learned how to arm them against most kinds of sea, and so we are doing that trick, and I would suspect, if it proves successful, I think it will, that this is what we'll do by and large. We'll rim all the continents with big high-duty cables running around them in the sea, and then splice out and send in messages that you're entitled to the last 20 or 30 miles to your shoreline. Then it's your business. The country then can do what it wants with the thing. So that's one of the things I think is coming up for sensible reasons, namely economics at the bottom. You don't get an argument with laying a cable. Try laying a cable across the United States. How many farms are you going to have to cross Kansas and so on? How much trouble are you going to have? A lot. But we used to lay cables that big. If I put a fair number of glass fibers in a cable, armor it heavily, and lay it once, I got an incredible bandwidth. And it may well be that we will put a set of north-south, east-west cables fundamentally across the continent, paying the price to lay them once and not have to lay them again in your lifetime because we just put down so much excess capacity. Now, we always did this with wires, but a cable that big, half as big is a lot of difference. Glass fibers, twice as much doesn't matter anyway because they're all a tenth of the diameter of a hair. Who cares? So that's one of the things you're going to see. Now, being in computers, I naturally ask myself, what's going to happen about computers? I suppose you know already that we are occasionally connecting various units on the floor with glass fibers. Although sometimes we do it by effectively radio across the tops, infrared signaling, much as some things work with trying to signal your television set. Some work by electric signals, some work by infrared, and so on. But now, if, as I said, glass has got great bandwidth, and bandwidth is the name of the game because it's really speed. When I say speed, I don't mean the velocity of light is faster. I mean I can get more bits in the same length of time. That's what I mean by fast communication. More bits in the same length of time. And light has clearly got much more frequency than electricity. And if I got fast bandwidth, I got faster computing elements. And if I haven't, I haven't. And we've been pushing against a pretty difficult situation. Will optics help out a lot? Can we make chips in which instead of having soldered metallic paths, we have optical paths? Let me draw you a picture of one. Here is a photocell. I happen to have, and you probably have seen, a hand calculator with no battery. So long as the light is shining on it, the power from that thing runs it. You've seen them have it, right? Well, I put the circuit here. I power it from here. I do not do power distribution wired to each one of the circuits. I put a light bulb. The light falls on all the chips. All the chips are locally powered. I get out of these costs of distribution. I get out of the trouble between distribution. Now I can do something else. I can put another chip here. And we've done things like this before. I can, instead of going from here to here, I can send a light beam up to there and put the next piece of circuit up there. And when I need it, come back down here. Now, light beams, if they're not too intense, go through each other. So instead of having a lot of wiring on this surface here, which, by the way, chips are just loaded now. Most of the acreage on chips is wiring, not active elements. I can put the wiring up this way. I get a tremendously higher density of parts. And I don't have to pay the price of power distribution. I just put a good-sized light bulb in and let it shine. Power distribution take care of. Two chips carefully mounted, carefully set up so they beam this way back and forth, focusing up and down with a very small glass lens. And I can get a tremendous higher density of parts without so much acreage going into wires from here to here to here. It's the only way I can do it. I can build the whole thing out of glass. These can be glass things, and these can be optical switches instead. I didn't say we're going to do it. I say there's one of the possibilities, because I ask myself, what will it mean to computing? Now, another one I want to get you to think about. We have a crossbar switch which connects a bunch of any one of 10 wires to any one of 10 wires down here, 12, or something like that. That's the essential way we've been switching for years and years and years. You know what a Fresnel lens is. You see them in lighthouses and so on. And you see them a lot of other places too. A Fresnel lens there, so this one is focused there and so on. And what I can do, presumably, is put a optical piece here. If I put a charge on it, it bends the light. I put another one the other direction, put it, bends the light. So by putting two charges, one on this one and one on one above it, I can change the path where it hits up here. I can change the path from here. I can build, I think, with time, 10,000 to 10,000 switch. The telephone company, again, has to work on it. It's too gorgeous. It can be nice and compact. 10,000 lines is a central office. I can do all the switching in a little thing like that. They've got to work on it. If they perfect it, how will you design a machine when I give you something like this, switching? Is the cheapest element out. After all, the telephone companies manufacture their own use, so you buy a couple from them. Okay, they charge you $5,000 or $10,000. The switching would now change the nature of computing again. I say switching, computing was changed completely when we got much more memory. If you get the price of switching down low, it has been the high part for a long, long while. If you bring that down to be very cheap, how will you design a computer? What would you do? Well, these are reasons why you want to look forward and do these things. I have not majored in glass fibers. I have done nothing but sit in the sidelines, read a little bit, and use my imagination a little bit so that I would not be left behind if this happens. If that does happen, I am prepared to say, oh yeah, I thought about that. Yeah, that's not so surprising after all. I will not be caught left behind. I want to come back to exactly, let's see if there's anything more I can do. I told you at the very beginning The purpose of this talk was to tell you how one person coped with the field of optical fibers. I did not spend any great amount of time. I did no experiments. I thought. At odd moments we'll walk the streets and various other things, and I thought about the nature of this and that. This is not the only new technology that's come up in my lifetime. In fact, my study of great contributions, when I ask, did you take a course in that? No, they had not. I've told you repeatedly, that which you learn from others, you can use to follow. That which you learn for yourself, you can use to lead. The leaders who do new things almost always do it based upon knowledge which they acquired for themselves, more or less. They didn't do all the experiments, but they kept up with things and saw possibilities, then went out and did it first. If you do it second, you might as well forget it. You either come in first or you don't come in first. We don't in life pay off very much for place and show. We play for win. The person who comes through with it first usually is a man of matter. The first person who articulates well an idea is the man who makes the contribution. Now, yes, there must be thousands of people who rally around the idea and accept it and act on it. But the leader is the guy who has the idea and articulates it carefully. And notice the second part. The history of science shows that a lot of people had ideas. They did not get them across. They rotted and had to be rediscovered. I told you the fast Fourier transform. If I didn't, I should have. It went back to Gauss. You see elements, a lot of pieces. They didn't exploit it. When Tukey really got after it, when the time was ripe, he did it, but now it's in widespread use. Well, my problem is exactly this. You will see a lot more than I did of new innovations. The pace of technology is indeed increasing. I had trouble keeping up. You're going to have more trouble. But if you will not keep up, two things are true. You'll be left behind and you will not be one of the leaders. You won't be one of the people who matter. And my task is to make you people who will matter. Plain and simple. Therefore, I've got to get you to be more open-minded and more aware of without taking time away from your main job. You have a main job now, typically. You've got to do it in spite of it. I told you a number of things. I warned you about wavelets. And I guess I did one at a time, and here I'm warning you about solitons as different methods of analysis and signaling. And the stuff we taught you in classical electrical engineering, all on a frequency approach, may be a fading thing. We're not doing that now. And what you do in the frontier of shipping signals across to Japan or other places by solitons, quickly will come up the question, why am I converting from solitons back to pulses? Well, why not keep the solitons going all the way? But pretty soon, the solitons are arriving in your house. And that's what's going to control the equipment. Now, just how it's going to be done, I don't know. I've thought about several things. With a glass fiber coming to your house, you want to do many things. Something to radio, something to television, something to this or that. One can build filters, a digital filter, and all I have to do is throw in different digits in the digital filter to get this band pass that I want. So each instrument, each thing you get has got a bandwidth of a given allocation. Those numbers are put in, you get that. Change the numbers, you got the other one. It could be that way, or it could be that the equipment you buy comes with its own filter automatically built in, and all you do is just plug it in and you don't even think. Now that's more wasteful of equipment, but it's easier on the human being. There's less thinking. How, if I had a general digital filter and I shared them all, how did those numbers get into the general filter for the particular new instrument you bought? If the instrument you bought comes with the filter attached to the end, then the cable goes in and it filters out what it wants. I'm inclined to think the second is what will happen, because not that it's cheaper in money in that sense, it's cheaper in human effort because humans cannot cope with all the kind of knowledge. You know the saying I've said several times. Children can run VCRs, old people can't. And you can verify for yourself. Very few old people can run a VCR. A kid of 6 walks in, bing, 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 he's got the VCR working. It's hard. You're going to face the same thing. And I'm pleading with you not to let yourself become obsolete, because if you become obsolete, not only is your career shot, but your life in some sense is. I think I may have told you. If I haven't, I'll tell you again. A friend of mine who taught me much about analog computers. I learned much from him. He was as smart as I was, though he didn't have a doctor's degree, but that doesn't matter. Doctor's degrees don't make you smarter. He was tied to the analog, and he would not really convert to digital. He really wouldn't do it. He was left behind. Management managed to find some other jobs which were interesting, and he was capable of doing some things, but finally management made it worthwhile for him to retire early. I retired early, as you know, to come here, do something exciting. Well, we had met on a few occasions. We changed cards until he died. He was somewhat disgruntled. His memory of his life, he was really squeezed out, and he knew. Never mind they gave him extra money and it made it nice to quit, all those nice things. He could not avoid knowing that he was squeezed out and the laboratories went on without him. I left at a time of my own choosing. I'm not guaranteeing you they wouldn't throw me out the next day, but I left before. I advise you always, if you're going to change jobs or do something else like that, do it at the time of your own choosing if it's only 10 seconds before you have to. It makes an enormous difference of how you see your life when you seem to have done the things you want to do instead of doing things you had to. And I'm coming down to the main theme of this thing. You are going to have to learn a large number of things, or you're going to be plain obsolete. And if you're obsolete, well, maybe you can enjoy fishing the rest of your life. I don't know. But I find it, my life is so much better than my friends. Well, he died anyway, so I can't follow all the way through, but I've seen other ones the same way. It's a very much you being what you think is in control of your life, which means you do keep up. Again, I did not spend a great deal of time on optical stuff. I watched do seminars here and there. I read literature occasionally. I noticed, but I was by no means an expert. But I did think about how it would affect my life. I've made projections. Some of these have not yet come true. 100,000 by 100,000 switch. I'm not sure they won't do it. 100 cells by 100 cells. A couple of those things here which will bend the light this much, that much. We know how to build those things. Boom. You've got this switching thing. It could change the nature of computation. It could change the nature of an enormous number of problems. That means you have to think about it. Now, if you are aware of these things in advance, somewhere in the back of your mind says, yeah, you know, if we had that, this vexing problem in the company could be solved that way. You win. If somebody else can buy it and installs it, you lose. Have I got the message across to you? See you next week then. Next week is beginning with computer-aided instruction. How much computers can help teaching. We got 2 pages.